Covalent or dative, which is the correct representation of protonated epoxides? So the stereotype behind organic chemistry is that it is terrible because students have to do things that they've never done before, like learning about the properties of functional groups, learning about IR spectroscopy, memorizing reagents, building molecular structures, and trying to find the products of reactions. However, the two main ones here is building molecular structures and how that impacts trying to figure out the products of reactions. A prime example of this is epoxide functionalization. So students are given an epoxide and they're asked to figure out which of the two products on the right-hand side is the major product. And they tend to get these questions wrong because of the way that the intermediate structure is represented, normally showing the protonated epoxide as having formal covalent bonds. Okay. During epoxide protonation, we have two potential forms. We have our covalent form, where each bond is formed covalently. We would think that the bond order would be around 1. And then you have your dative structure, which has partial bonds because the bond order would be less than 1. So for the materials and methods, I modeled and compared the neutral and the protonated forms of ethylene oxide, propylene oxide, and isoprene oxide. And we measured the bond order, the bond length, and the atom charges. Okay, so starting off with the atom charges, whenever methyl groups were added, we saw that our carbon-2 became more positive, starting at 0.05 and ending at 0.33, and then our carbon-1 became more negative, starting at 0.05 and ending at negative 0.01. So whenever we looked at the bond length with the protonated epoxides, we saw that the oxygen C2 bond length was increasing whenever methyl groups were added, suggesting that it could possibly be weakening. And then the oxygen C1 bond lengths were actually decreasing, suggesting that that could be strengthening. So since there was weakening in the bond length, we ran some bond order calculations, and as we expected, the bond order between oxygen and C2 was decreasing, so that was weakening, and then the bond order between oxygen and C1 was increasing, so it was strengthening. So the data shows that the dative form might be the best way of representing this instead of the covalent form. The bond between the carbon-2 and the oxygen is not a full bond, it's weakened. And although the covalent form is the most convenient, we need to emphasize what's actually happening and how protonation can actually alter the shape and properties of the molecule. Our study does have some limitations. We use semi-empirical calculations, so PM6, and that can be inaccurate. So in the future, we could use a higher level of computational theory. The calculations were also in vacuo, which means that no solvent effects were considered. So in the future, we could question how do solvents influence structures. And then lastly, we only examine epoxides, so we could figure out if other systems in the future have the same effect.